You deploy an autonomous agent. It runs flawlessly for the first 50 steps, executing tool calls, evaluating logic, and passing data. Then, on step 51, it hallucinates a parameter, goes off script, and halts completely. To find out what went wrong, most engineers do what they have always done for traditional microservices. They open a flat, chronological JSON log and start scrolling. JSON, or JavaScript Object Notation, is a standard text format used to store and transport execution data. But chronological logs fail when applied to large language models, or LLMs. A large language model is a type of artificial intelligence trained on vast amounts of text to understand and generate human-like language. A sequential list tells you what happened, but it obscures the probabilistic reasoning and shifting context window that actually drove the agent's failure. Operators routinely spend upwards of 30 minutes manually stepping through thousands of execution events. They are searching for a single hallucinated string buried in a wall of raw text. To actually observe and fix these systems, engineering teams must move beyond flat timelines. Execution traces must be reconstructed into causal dependency graphs, structures that link outcomes directly to the specific decisions that caused them. Agent Debugger is an open-source system built to apply academic tracing frameworks to this exact architectural problem. Debugging autonomous AI is no longer a text search problem. It is a problem of causal inference and state inspection. Instead of reading forward from the start of a log, this structure allows you to start at the observed failure and trace backward to find a root cause. Agent Debugger extracts explicit evidence links, or provenance, from the raw execution traces to build this dependency graph automatically. Provenance is the record of the origin and history of a specific piece of data or decision. The result is a decision tree. It isolates individual LLM decisions and groups them directly with the specific tool nodes and data outputs they generated. The graph distinctly separates routine execution errors, like a timed-out API call, from actual policy interventions, like a safety guardrail blocking a dangerous prompt. The structure allows an engineer to instantly isolate the exact node where the agent's logic diverged from the expected behavior. Once the causal graph is built, the debugger's causal analysis module activates the Why Did It Fail engine. This engine scans the causal graph and uses an LLM to generate natural language explanations, ranking the most likely candidate root causes for the failure. Each hypothesis receives an explicit confidence score. The system calculates this by measuring the proximity of the upstream deviation to the failure and the overall impact of that specific node on the graph. These natural language summaries map directly to the underlying evidence nodes. Operators do not have to blindly trust a summary. They can click the explanation to reveal the exact raw data that generated it. This reduces root cause identification from 30 minutes of manual reading to less than 30 seconds. Automated root cause analysis shifts the focus away from finding the bug, allowing the engineer to focus entirely on fixing the logic. Identifying the error is only the first step. To verify a fix, you need the ability to reproduce the failure through time travel replay. Simply replaying a text log is insufficient for non-deterministic environments. Because an LLM might generate a different response on a second run, the exact memory state of the agent must be restored. To achieve this, the system captures a base checkpoint state. This involves serialization, the process of converting complex data objects into a format that can be stored and later reconstructed. This snapshot is saved to the database and injected back into a live Python execution thread. Using the traceContext.restore method, the system rewinds the agent to the precise microsecond before its logic diverged. From that restored state, the engineer can fork the execution, apply a fix to the prompt or the tool, and test the outcome immediately. Time travel debugging turns transient LLM hallucinations into reproducible, testable states. Even with state restoration, watching a 10-minute agent loop play back linearly is an unviable waste of engineering time, a problem known as replay fatigue. The debugger implements the MSSR framework, Memory-Aware Adaptive Replay, to collapse low-value segments of a trace. The system uses an important scoring algorithm to evaluate structured event fields. It prioritizes high-value anomalies over routine events. When you initiate playback, the cursor automatically skips over standard events. It stops exclusively on low-confidence nodes and safety policy escalations. Adaptive replay ensures that engineers only spend their time reviewing the exact moments the agent struggled or escalated. On a larger scale, engineering teams often solve the same tool loop errors or hallucinations across different sessions, losing that knowledge once the session ends. The debugger addresses this by implementing failure mem, which utilizes cross-session vector search. Vector search is a method of finding similar items based on their mathematical representation in a high-dimensional space. As an agent runs, the system maps real-time failures against historical failure-to-fix pairs stored in the database. When a match occurs, operators see the similarity score alongside the exact code snippet or prompt adjustment that previously resolved the issue. This transforms transient debugging efforts into a compounding knowledge base for the entire engineering team. Implementing these workflows requires a physical architecture built for enterprise environments. The Local-First SDK integrates via framework adapters for LangChain and Pydantic AI. Data enters a redaction pipeline, actively scrubbing PII before persistence. Clean data routes through a Redis buffer to handle high-volume telemetry safely. Finally, PostgreSQL enforces strict multi-tenant isolation. From this secure storage, the causal engine and UI query structured data to render causal graphs and power time travel. This architecture ensures privacy is never compromised for observability. The ultimate value of this system is comparing a failed trace side by side with a successful patched trace to definitively prove why a change worked. Abandoning flat chronological logs in favor of queryable structural graphs saves hours of engineering time. You are left with evidence-grounded decisions, adaptive replay timelines, deterministic state restoration, and cross-session failure memory. Treating these complex AI executions as navigable, reproducible graphs is the only reliable way to scale autonomous systems. Effective observability removes the magic from AI development, reducing non-deterministic agents back to a rigorous, debuggable engineering discipline.